Imagine if Earth were much, much closer to the Sun. So close that an entire year would only last a few hours. So close that gravity has locked one hemisphere in a permanent searing daylight, and the other in eternal darkness. So close that the oceans boil away, rocks begin to melt, and the clouds rain lava. While nothing like this exists in our own solar system, planets like this, rocky, roughly Earth-sized, extremely hot, and close to their stars, are not uncommon in the Milky Way galaxy. But what are the surfaces and atmospheres of these planets really like? Join us today as we are going to talk about how NASA's James Webb Space Telescope is about to provide some answers by discovering two new super-Earths that will shock the entire space industry. The James Webb Space Telescope, or JWST, has been in space for about 6 months, which is just a fraction of the time NASA spent designing and building it. All that effort is about to pay off, though. NASA designed the JWST as a follow-up to the hugely successful Hubble Space Telescope. While Hubble needed a service mission after launch to work correctly, Webb appears to be a prime example of optical perfection. NASA reports the telescope's instruments are diffraction limited, which means it's as good as it can possibly be given the size of the mirror. So far, we've only seen a few test images from Webb, but they already show how much more powerful it is than the past instruments. That could be a boon to the study of exoplanets, which are too dim to be observed in detail. However, Webb has a much larger mirror than even Hubble, and it can peer deeply into the infrared part of the light spectrum, which certainly is good news for discovering new Earth-like planets. Therefore, exoplanets will be among the targets in JWST's Cycle 1 round of observations. The exoplanet community elected Natalie Batalla to lead transit spectroscopy studies of these gas giants as part of these early observations. Her team will also develop data pipeline and processing techniques for the community to copy. Cycle 1 also includes observations for specific groups of astronomers. Last year, more than 2,000 groups submitted proposals to use JWST in the first cycle, but a time allocation committee selected 266. Dozens of these programs will look at planets, and out of all the exoplanets that JWST look at in Cycle 1, Natalie Batalla reckons that the 3 TRAPPIST planets that orbit their star's habitable zone probably have the best shot at featuring detectable biosignature gases. The TRAPPIST system is unique in that the star is very small, and so the relative feature size of the atmospheres doesn't need to be big in order for you to be able to see it, she said. Whether Webb has a realistic chance of spotting biosignature gases is debatable, however. Often, the controversy comes up over the definition of oxygen, she said. Oxygen absorbs 1 infrared wavelength in Webb's range of sensitivity, and so theoretically, an oxygen-rich transiting planet could put a noticeable dip in its star's spectrum at that wavelength. However, she said, the wavelength is just at the edge of where the detector loses sensitivity. Other types of combinations of gases will be easier to detect, but might be harder to definitively attribute to life. So Webb might just identify possibly living planets, which could then be examined more closely with future space telescopes. In addition, NASA's Nancy Grace Roman Space Telescope, slated to launch later this decade, is mostly designed to study dark energy, while on the other hand, Earth-like exoplanets are the purview of the Future Telescope concept provisionally known as LUV-X, an ultraviolet, optical, and IR telescope that will launch in the mid-2040s. Therefore, what we will look at then depends on what we learn in the next few years. Now, with its mirror segments beautifully aligned and its scientific instruments undergoing calibration, NASA's James Webb Space Telescope is just weeks away from full operation. Soon after the first observations are revealed this summer, Webb's in-depth science will begin. Included in the investigations planned for the first year are studies of 2 hot exoplanets classified as super-Earths for their size and rocky composition: the lava-covered 55 Cancri E and the airless LHS 3844b. Scientists will train Webb's high-precision spectrographs on these planets, with a view to understanding the geologic diversity of planets across the galaxy, as well as the evolution of rocky planets like Earth. So let's take a look at these one by one. Superhot Super-Earth 55 Cancri E. 55 Cancri E orbits less than 1.5 million miles from its Sun-like star, completing one circuit in less than 18 hours. With surface temperatures far above the melting point of a typical rock-forming mineral, the day side of the planet is thought to be covered in oceans of lava. Planets that orbit this close to their star are assumed to be tidally locked, with one side facing the star at all times. As a result, the hottest spot on the planet should be the one that faces the star most directly, and the amount of heat coming from the day side should not change much over time. But this doesn't seem to be the case. Observations of 55 Cancri E from NASA's Spitzer Space Telescope suggest that the hottest region is offset from the part that faces the star most directly, while the total amount of heat detected from the day side does vary. So, does 55 Cancri E have a thick atmosphere? One explanation for those observations is that the planet has a dynamic atmosphere that moves heat around. 55 Cancri E could have a thick atmosphere dominated by oxygen or nitrogen, explained Renyu Hu of NASA's Jet Propulsion Laboratory in Southern California, who leads a team that will use Webb's Near-Infrared Camera, or NIRCam, and Mid-Infrared Instrument, or MIRI, to capture the thermal emission spectrum of the day side of the planet. If it has an atmosphere, Webb has the sensitivity and wavelength range to detect it and determine what it is made of, Hu added. In addition, there is also a speculation according to which it is raining lava in the evening on 55 Cancri E. Therefore, another intriguing possibility, however, is that 55 Cancri E is not tidally locked. Instead, it may be like Mercury, rotating 3 times for every 2 orbits. As a result, the planet would have a day-night cycle. That could explain why the hottest part of the planet is shifted, explains Alexis Brandecker, a researcher from Stockholm University who leads another team studying the planet. Just like on Earth, it would take time for the surface to heat up. The hottest time of the day would be in the afternoon, not right at noon. Therefore, Brandecker's team plans to test this hypothesis using NIRCam to measure the heat emitted from the light side of 55 Cancri E during 4 different orbits. If the planet has a 3-to-2 resonance, they will observe each hemisphere twice and should be able to detect any difference between the hemispheres. In this scenario, the surface would heat up, melt, and even vaporize during the day, forming a very thin atmosphere that Webb could detect. In the evening, the vapor would cool and condense to form droplets of lava that would rain back to the surface, turning solid again as night falls. Now let's take a look at the second exoplanet on the list, which is somewhat cooler super-Earth LHS 3844b. So while 55 Cancri E will provide insight into the exotic geology of a world covered in lava, LHS 3844b affords a unique opportunity to analyze the solid rock on an exoplanet's surface. Like 55 Cancri E, LHS 3844b orbits extremely close to its star, completing one revolution in 11 hours. However, because its star is relatively small and cool, the planet is not hot enough for the surface to be molten. Additionally, Spitzer observations indicate that the planet is very unlikely to have a substantial atmosphere. So, what is the surface of LHS 3844b made of? Well, we won't be able to image the surface of LHS 3844b directly with Webb. The lack of an obscuring atmosphere makes it possible to study the surface with spectroscopy. It turns out that different types of rock have different spectra, explains Laura Kridberg of the Max Planck Institute for Astronomy. You can see with your eyes that granite is lighter in color than basalt. There are similar differences in the infrared light that rocks give off. Kridberg's team will use MIRI to capture the thermal emission spectrum of the day side of LHS 3844b, and then compare it to spectra of known rocks like basalt and granite to determine its composition. If the planet is volcanically active, the spectrum could also reveal the presence of trace amounts of volcanic gases. So the importance of these observations goes far beyond just two of the more than 5,000 confirmed exoplanets in the galaxy. They will give us fantastic new perspectives on Earth-like planets in general, helping us learn what the early Earth might have been like when it was hot like these planets are today, said Kreidberg. Therefore, these observations of 55 Cancri E and LHS 3844b will be conducted as part of Webb's Cycle 1 General Observation Program. And if everything goes well, it will turn out to be a huge success for the successor of Hubble and scientists who designed it for decades. And this is it for today. What are your thoughts on today's video? Also, don't forget to give this video a thumbs up, subscribe to the channel, and ring the bell icon for more amazing videos about space. And thank you for watching.